Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics, Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's presentation on random variables and probability distributions. And the overview of today's presentation. First, I would like to explain what is the probability and the definitions which are needed to understand the actual concept of probability. So, the introduction to probability with some examples, and then introducing random variables, the definitions and different types of random variables. Now, experiment, an activity which is conducted and whose results are to be noted, that is called experiment. An activity which is conducted and also the results are noted is called an experiment. And this experiment can be repeated any number of times also. So, that is called number of trials also. And then experiments are two types, deterministic experiments and non-deterministic experiments. These non-deterministic experiments are also called probabilistic experiments. And let us define these two. The deterministic experiments, the outcome or the result is unique and the result can be predicted. So, the experiments in which the outcome or result is unique or the outcome can be predictable are called deterministic experiments. For example, our laboratory experiments, and some examples are given here: the boiling point of a liquid, the current passing through a circuit, or the Ohm's law I equal to E by R determines the current uniquely. In all these cases, the result is unique. So, the experiments in which the result or outcome is unique or can be predictable are called deterministic experiments. And coming to the next definition, non-deterministic or probabilistic experiments. The experiments in which the outcome or result is not unique, that means there may be number of possibilities, number of outcomes, number of results. So, the result cannot be predictable. A simple example is lifetime of a computer, tensile strength of a beam, or defective item in a lot of items, and tossing a coin or throwing a die. All these comes under probabilistic experiments. So, in probabilistic experiments, the result or outcome is not unique and we cannot predict the solution also. And now, sample space. For example, let us consider a probabilistic experiment. That means the result is not unique. And now, let us form a set with all the outcomes of the experiment. So, that set is called sample space. Simply, the set of all outcomes or results of a probabilistic experiment is called sample space, and it is denoted by capital S, the letter capital S. And here are some examples. Consider the experiment of tossing a coin. Here the outcomes are either head or tail. So, the result can be either head or tail. So, let us write these two outcomes in a set. So, and denote it by capital S. Capital S is equal to either head or tail. This is called the sample space of this particular experiment of tossing a single coin. Similarly, let us consider the experiment of throwing a single die, and all of you know a die has 6 faces and having the numbers from 1 to 6. So, the outcomes are either 1 or 2 or 3 or so on or 6. There are 6 outcomes. Let us form a set with all these outcomes. So, this set capital S is the sample space of the experiment of throwing a single die. Similarly, we can define some other examples of tossing 2 coins, tossing 3 coins, or tossing 2 dice, etc. In all these experiments also we can find the outcomes and we can find the sample space S. Simply the sample space is the set of all outcomes of an experiment. Now, the sample size. The total number of elements of sample space is called the sample size. It is denoted by N of S. For example, in the experiment of tossing a coin, there are 2 outcomes H comma T. So, N of S is 2. That means the sample space contains 2 elements. So, the total number of sample points or the total number of elements of a sample space is denoted by N of S. And next, throwing a die. Here there are 6 outcomes. So, S contains 6 elements. hence n of s is 6. Some other example. Let us consider the experiment of tossing two coins. If two coins are tossed, then the results will be the combinations of the two coins. For example, both coins may show head, or both coins may show tail, or first coin head and second coin tail, first coin tail or second coin head. So, there are 4 outcomes of this experiment, hence n of s is 4. Previously, if one coin is tossed, then there will be only 2 elements. So, n of s is 2, and which can be written as 2 power 1. Here 2 coins are tossed and there are 4 outcomes. So, n of s is 4, which can be written in the form 2 square. Let us consider the experiment of tossing 3 coins, and here the combination of 3 results. So, all 3 coins may show heads, all 3 coins may show tails, like that there are 8 outcomes. So, n of s is 8, which can be denoted by 2 power 3. So, here if n coins are tossed, then the sample space contains 2 power n elements, n of s is 2 power n. And another example of throwing 2 dice. If 2 dice are thrown, let us fix the first die, the number on the first die as 1, and change the number on the second die. So, 1 1, 1 2, 1 3 and so on 1 6, total 6 elements. Let us fix the element on the first die as 2. So, 2 1, 2 2 and so on 2 6. Similarly, 6 1, 6 2 and so on 6 6. So, in each row there are 6 elements and there are 6 rows. So, the total number of elements of the sample space is 6 into 6, 36 elements. So, n equal to, or the sample size n of s is 36 6 square. So, the size of the sample space is 6 square. Similarly, if n dice are thrown, 6 power n is the number of elements of the sample space. Now, coming to the next definition, event. Any non-empty subset of a sample space is called an event. Even we can consider an empty subset also, which comes under a special category, which is the null set. So, simply we can say any subset of a sample space is called event. For example, let us consider the experiment of tossing a single coin. Then the sample space S contains 2 elements H and T. Now, if I consider my event E as getting head, then E contains only our favorable outcomes. So, E equal to H. So, this is called an event of getting head, and which comes from the actual sample space S itself. So, that means here E is the subset of S. So, any subset of a sample space is called event. It can be some non-empty or empty also. That empty subset is a separate case. And now, throwing a die. Let us consider the experiment of throwing a die. Here the sample space contains 6 elements 1 to 6. Now, let A be the event of getting an even number. So, out of these 6 elements, there are 3 even numbers. So, let us form a set with these 3 even numbers. So, capital A equal to 2, 4, 6. This is the event of getting an even number. And similarly, event of getting an odd number. Let B be the event of getting an odd number. Then there are 3 odd numbers in the sample space 1, 3 and 5. So, the elements of B are 1, 3 and 5. Similarly, event of getting a prime number, and all of you know that 2 is the least prime number and 1 and only 1 even prime number. So, in the set S there are 3 prime numbers 2, 3 and 5. So, the set C is 2, 3 and 5. This is the event of getting a prime number. So, like this we can define an event as any subset of the sample space. And now, coming to the actual definition of probability, which is called the classical definition of probability. Let us consider an event capital E. The probability of an event is denoted by P of E and is defined as N of E by N of S. And just now we have discussed n of s is the total number of elements of the sample space of the given experiment. So, this n of e is the favorable number of cases of our particular event E. So, n of e by n of s gives the probability of the event E, which can be defined as the favorable number of cases by total number of cases, or favorable number of outcomes by total number of outcomes, favorable number of results by total number of results. A simple example, let us consider the experiment of tossing a coin. There are two outcomes h comma t. So, if you want to find the probability of head, since there are only two elements in the sample space, 2 is the total number of outcomes, and out of those two, which is favorable for us? So, getting the result head, that means there is only one possibility. So, 1 by 2 is the probability of getting head. Similarly, probability of getting tail, again 1 out of 2 total cases. Let us consider the experiment of throwing a single die. If a single die is thrown, there are 6 elements, and if you want to find the probability of getting number 3, the result as 3, there are total 6 outcomes. Out of 6 outcomes, this 3 is only the favorable case for us. So, one way, total favorable number of ways by total number of ways. So, 1 out of 6. Similarly, if you want to find the probability of getting number 4, that is also 1 by 6, probability of getting number 6, 1 by 6, and so on. And if you want to find the probability of getting an even number, so how many even numbers are there? There are 3 even numbers. So, probability of getting even number is 3 by 6, which is 1 by 2. So, the probability of getting an even number is 1 by 2. Similarly, odd number, there are 3 odd numbers. So, 3 by 6, which gives 1 by 2. Let us consider a simple example. 2 dice are thrown. 2 dice are thrown. Now, the question is, what is the probability of getting sum 9? So, the experiment is throwing 2 dice. Now, we need to calculate the probability of getting sum 9. So, if 2 dice are thrown, then the sample space contains 36 elements, just now we have discussed. So, starting from 1 1, 1 2 and so on 1 6, 2 1, 2 2 and so on 2 6, like this, the last number 6 1, 6 2 and so on 6 6. So, the total number of sample elements n of s is 36. There are 36 outcomes. There are 36 possible outcomes of this experiment. Now, we need to calculate the probability of getting sum 9. So, let E be the event of getting sum 9. So, if you find the elements of this E using the definition of classical definition of probability, we can find the probability of getting sum 9. So, in how many cases we get the sum 9, that we need to calculate. For example, here let us consider the first row. In the first row, the maximum element number is 6 and minimum is 1. And what is the total? The sum of these two elements is 7, but here we need sum 9. So, using the first row elements, we can't get the sum 9. Similarly, second row, maximum is 6, minimum is 2. So, 2 plus 6 is 8. So, we won't get sum 9. So, we will get sum 9 from the third row itself. If the outcome is 3 comma 6, the sum is 3 plus 6 is 9. Similarly, 4 comma 5, 5 comma 4, 6 comma 3. In all these cases, the sum is 9. So, the event E has the elements 3 6, 4 5, 5 4 and 6 3. How many elements are there in the event E? 4. In 4 outcomes, we will get sum 9. Now, using the probability of an event, the classical definition of probability of an event, P of E is N of E by N of S. So, There are 4 favorable cases out of 36. So, 1 by 9 is the probability of getting some 9. Like this, we can calculate the probability of a particular event using the classical definition of probability. Now, the next concept is random variable. In some experiments, the outcomes are numeric, whereas in some experiments, they are non-numeric. For example, let us consider the experiment of tossing a coin. In the experiment of tossing a single coin, what are the outcomes? Either head or tail. So, this is the sample space of this experiment S equal to h comma t. So, here the outcomes are non-numerical values. These are not numerical values. For example, if you consider the experiment of throwing a die, then there are 6 possibilities of getting any number from 1 to 6. So, the outcomes or results are numerical values, whereas here the outcomes are non-numeric. Similarly, if you consider an experiment of tossing 2 coins, then the sample space contains the combinations of the 2 results. Both are heads, one head, one tail, one tail, one head, and both are tails. And in this case also the outcomes are not numeric. Now, we assign a real number to each and every outcome of such experiments. We assign a real number to each and every outcome of such experiments. So, we assign a real number to each and every outcome of the experiment. This rule of assigning a real number is called random variable. This rule of assigning a real number to each and every non-numeric outcome is called random variable. In another way, we can define the random variable in a mathematical notation as random variable is a function defined from the sample space capital S to the set of real numbers R. That means, to each and every sample point of this S, we assign a real number from the set of R. So, f is a function defined from sample space S to real number set R. And random variables are denoted by capital letters X, Y, Z and so on. And for example, if you consider the previous tossing 2 coins, so the outcomes are both are heads, one head, one tail, one tail, one head, both are tails. Now, first we need to define the random variable. Let capital X be a random variable that denotes number of heads. Let capital X be a random variable that denotes number of heads. Then X takes the values, X takes the values. Now, here you see, if 2 coins are tossed, maximum we will get 2 heads. We won't get 3 heads since only 2 coins are tossed. So, maximum value is 2. We may get 2 heads or 1 head, one tail, or both are tails means complete failure case, 0 heads. So, X takes the values either 0 heads or 1 head or 2 heads. So, like this we assign a real number to each and every outcome of the experiment. Here you can see the number 2 is assigned to the outcome h comma h, and for these 2 the number 1 is assigned, and if both are tails, that itself means 0 heads. So, 0 is assigned to this outcome. Hence, X takes the values 0, 1 and 2. This is the definition of random variable. And coming to the types of random variables, there are 2 types of random variables, discrete and continuous. Discrete random variable and continuous random variable. A discrete random variable is a random variable in which X takes finite number of values. So, simply if X takes finite number of values, then it is called a discrete random variable. The previous example, here X takes 0, 1, 2. So, total how many values? 3 values, where 3 is a finite value. So, X takes the values x1, x2 and so on xn, n values, where n is a finite number. So, In this case, this capital X is called a discrete random variable. So, the definition is very simple. If x takes the finite number of values, then x is called a discrete random variable. At the same time, if x takes infinite number of values, then that random variable is called a continuous random variable. X takes infinite number of values. So, that we can denote that as capital X equal to small x that belongs to a comma b. Simple example, x belongs to 0 comma 1. So, if x belongs to 0 comma 1, here 0 and 1 are real numbers, and we know that between any two real numbers there exists infinite number of real numbers. So, if x belongs to 0 comma 1, x takes infinite number of values, hence x is not a discrete random variable, it is a continuous random variable. So, if x takes finite number of values, then x is called discrete, and if x takes infinite number of values, then it is called continuous random variable. These are the two different types of random variables, and in today's session we have discussed the introduction to the probability and the definitions which are required to understand the concept of probability, and then we have discussed probability distributions and types of distributions also discussed. Thank you.